All right, so this is our second talk for this session. Our next speaker is Xavier Leroy, who is a research director at Inria, Paris. Xavier has done a lot of work, has contributed a lot to the fields of static analysis, formal verification, and he has done some work that is complementary to what we actually saw earlier. Joseph Tesseroti talked about the verification of the compiler and mentioned that there is this other component, which is the verification of the inference. And so Xavier has done work on this and is going to present his work towards verified stochastic variational inference for probabilistic programs.
Okay, many thanks, Jean-Baptiste, for the introduction, and thanks a lot, Xavier and Jean-Baptiste, for the invitation. Yes, thanks. So first of all, I would like to mention this is joint work with Wanyol Lee, Hangul Liu, and Hong Sok Yang, who are Hong Sok in particular is a long-time PL expert who moved to probabilistic programming with a lot of PL expertise and also involved the three of us. So I am more of a static analysis person, so many of the concepts of probabilistic programming are still new to me from time to time. So what about our topic today? So as we have discussed in a previous talk, so probabilistic programming is about computing over distributions. And probabilistic programming languages have some basic features like sampling or conditioning, which have been discussed already, and also some advanced features like learning model parameters. And this is going to be the topic of my talk. So in this work, we will mostly discuss in the context of Pyro, but what I will say is also actually valid for other languages. So what is variational inference? So essentially the goal of variational inference is to start with a potentially complex model which describes some system with some set of data, of real data observation, which typically relies on sampling and also on noisy measurement. And we usually want to have some more abstract, higher level view of what this model says. So we bring a second program to the party, which is going to be referred to as a guide in this talk, which has a bunch of parameters. So it's actually a family of programs, not just one. And the goal of inference is to find optimal values of those parameters so that we get a guide that is hopefully going to be much simpler than the initial model and that is going to describe the model as well as possible. Okay, so if we just look at a very basic example of application of this methodology, you may start with a coin that you know may have some little bias. So you have a prior that it should not be too much biased. You describe a model which describes a tossing experiment. You toss the coin a bunch of times, and essentially you would like to know what is the actual bias of that coin. So you are just going to write a guide which describes an ideal biased coin with an identified bias as a parameter, and the inference will tell you what the parameter should be. Okay, so variational inference is not simple at all. It relies on fairly complex and involved algorithms, which are going to do collections of sampling over a large number of executions together with their probability density, and it will perform some global optimization with typically some form of gradient descent. So the problem is that actually these algorithms will rely on a bunch of mathematical theorems which are far from obvious when you look at the code of the program. And this is going to be what we are going to look at today. So here is a high-level view at the journey we have in front of us. So we will essentially try to formalize variational inference, well, stochastic variational inference. But before we do that, as a PL person, I like to have semantics. So we will start with the conventional semantics, which is inspired from the textbook, which is essentially cosine semantics. Then we will move to a slightly different semantics that will be a little bit more adapted to the problems that we would like to solve. And based on this, we can formalize SVI. But SVI may actually not work if we just don't have model and guides that satisfy accurate assumptions. So we will also come up with semantic conditions which imply that SVI is well defined. So note we have an implication here. It's not an equivalence. So it could be that our semantic conditions are violated and still SVI will work. Okay? But semantic conditions are just a bunch of lines on the paper. So for the programmers, it's not always very helpful to just have these probably abstract conditions that have to be satisfied on a program, verified on a program. That's also not so trivial. So we will also come up with conservative static analysis by abstract interpretation that tries to prove that these semantic conditions are satisfied. So since there are quite a few steps in this journey, I may actually just walk quickly through some of these, but do not hesitate to ask questions anytime. Okay, so before we start this journey, we just have to look essentially what kind of problems we are looking at, and we will look at a few examples. So before that, I will just show the kind of program we are manipulating. So it is Pyro code. So just to become familiar with the syntax, we are just going to start with very basic model, which is written here, which samples one random variable v with normal distribution. So the meaning of this program is we are going to sample a value based on a distribution, and essentially we can plot the distribution over execution based on the final value of variable v that is here. Okay, so that's very conventional. Then we can add the second construction of probabilistic programming, which is scoring. So here I just take the same model and I make it a little bit complex. I just add some observation to it, but to put a little twist to this observation, I will make the observation depend on the sign of v. So if v is positive, I will just let some observation say that we observe that, wait, I think I have typo. Okay, sorry, this should be v. So some observation that v should be close to 1 with some normal distribution with standard deviation 1. And if v is negative, we are going to make the observation that it should be minus 2, with also normal distribution, standard deviation 1. So obviously it is more likely that the first condition holds. So essentially we have some conditioning in progress, which will put more weight on the executions where v is positive and less weight on the executions where v is negative. So the actual distribution we have on v corresponds to something a little bit like this plot. So now let's get to what SVI will do. So we have here something that is, well, not very complex as a model, but let's imagine we would like to describe this in a more concise manner. So essentially what we are going to do is to try to identify, some program that describes in an accurate way the grain curve here, but in a more concise way than this Pyro model. So we are going to come up with the notion of guide. So what is a guide? It is a second program with some parameter, which will typically be called theta. So we have this theta here, which is declared as a parameter for Pyro. So actually this just tells Pyro during the optimization, you should optimize over this guy theta. And essentially it will also define variable v by sampling some normal distribution over v. I just estimate that probably I can take this grain curve here and get rather close to it with some normal distribution. So I will have a curve that is going to be centered around some positive value, but which should not be too high either, because it's very likely that v is positive and not too far from 0. Okay? So here is one instance here in red, which is not too far from what we intuitively expect based on our knowledge of the problem. So how will SVI be defined? Well, before we define SVI, we have to look at what we can optimize about these two programs. So essentially, we just said we would like them to be as close as possible to each other. So in order to do that, we have to define some kind of distance. And this kind of distance is typically KL divergence, which is defined as the expectation with respect to the distribution induced by one of the two programs of the log of the quotients of the two probability distributions of model and guide. So, and that can be described in continuous case as some kind of integral. So this is well and nice, except that for this to be defined, we actually need some condition on P0 and P1, which is going to play a great role a bit later. So in fact, what you need is you need P0 to be absolutely continuous with respect to P1, which means that if you have measurable observation x and P1 of x is 0, then P0 of x should also be 0. Otherwise, the quotient will just make KL divergence undefined. Okay? So, and it's not exactly a distance, it's always positive, and it is 0 if and only if P0 and P1 are almost equal everywhere on all measurable sets, but it's not quite, it does not satisfy triangular inequality, so it's not exactly a distance. Okay? So based on this, optimization will just try to find some value of theta, which makes the KL divergence of the distribution induced by the model and the distribution described by the guide with instance theta as close as possible. So if we plot the KL divergence for the simple example I made with respect to theta, we get a curve a bit like this. And indeed, you can see that there is a minimum somewhere that is with a value around +2 or something like that. Okay? And the optimization objective, which we hope for SVI to solve, is to identify some value theta that will minimize this distance. Well, pseudo distance. It's not exactly a distance. Okay, so what is the algorithm? Well, it's going to be some kind of gradient descent. So the implementation will have to select some initial value of theta. So it will select some theta 0, and it will do some stochastic optimization. So it will compute a number of times some approximation of the gradient, which is typically done by generating a number of samples and just computing an approximation of the gradient based on those samples and updating theta with this using some kind of learning rate. And hopefully, after a number of samples, of iterations, we are going to get sufficiently close to some optimum. So the beauty of this is that this can actually be implemented in just a few lines in Pyro. You just have to call some engine which takes as parameters your model, your guide, and a bunch of parameters that you can use to tune the optimization process. And you don't have to do much more than that. Don't worry, you just send this, and you hope that it works. So will it work? Well, that's a good question. So actually, if we ask it, well, you can expect that the answer is maybe not always. And indeed, so here is an example, which is actually some excerpt of some examples that were on the Pyro web page at some point. Maybe they were removed now. So we have a model here, which, I mean, I just simplify it a lot, so I ignore some part. At some point, we sample some variable, some random variable sigma using some uniform distribution between 0 and 10. And later in the guide, I also have sigma that is also sampled, but this time we use normal distribution with whatever parameters. And in fact, if we just look at those two programs, the problem that we have here is that KL divergence is not defined anymore. The reason for that is because essentially the domain of the sigma in the model is 0, 10, because we sampled uniform distribution, and in the guide, it is a whole real line because we have used normal distribution. Okay? So in other words, what we have here is a violation of this absolute continuity requirement that I pointed out for KL divergence to be defined at all. So what this means is that in this case, you may have a failure for KL divergence to be defined. So that's already a first problem, which means that in that case, you can expect SVI to produce various results that have no relation with respect to what you expect. And actually, that's not all. You have other issues that could come up also even if you have absolute continuity, two probability distribution. It does not guarantee that you can integrate the log of the quotient of the two distributions. And even then, more problems can occur if you have differentiability issues of KL divergence. If KL divergence is defined, even if you can integrate, you can define it and everything, but you cannot differentiate it, then you have also the chance that stochastic variational inference will produce some result that is not appropriate. One more issue that could happen is that when you compute this gradient, since we cannot compute it symbolically in general, we typically use some kind of stochastic approximation. This stochastic estimate should also not be biased, otherwise you could have incorrect results. So in practice, what happens when some of these issues come up? Well, various things can come up. Well, the best thing that could happen is a crash, because in this case, you know that you have to fix something. But you may also observe some more confusing problems like divergence of the inference engine. Well, you also notice that something goes wrong, but it's less clear what is the problem. Performance bugs are hard to understand in general. Or you can even get some result which has incorrect meaning. And that is a lot worse because there is no warning. You just get some answer and you have to really look into the answer to find out that it's just not making sense. Okay, so this is the starting point of our work, to try to find some kind of answer to this problem. So now I will just go through the journey I just presented in the beginning of the talk. I will skip some of the steps because we cannot quite go through all the details, but I will try to give a flavor of the whole story. So first, in this description, we will use some probabilistic programming language, which is imperative language with sample and score with just normal distribution. So I keep it very simple. It corresponds to the language that Gilles, well, I think Gilles did not have score, but except for this, it's very similar to what Gilles presented this morning. And we are going to give a semantics to that, because without semantics we cannot do any PL verification. We cannot do static analysis. So we have to first have a semantics, and we are going to start with a semantics that is recognized as quite a common approach. So we are going to use one of the semantics proposed by Cozen in the very early days, where people started to study how to give meanings to programs with probabilities. So we are going to use semantics where we have a notion of memory, okay, which describes the states of the program, which is what we are used to in conventional programming, and we are going to adjoin to that some random database that is going to start to accumulate all the samplings that are done by the program during the execution. Okay? And essentially, when we compute such an execution, so we are going to start with a state which has a memory state, an empty random database, and we are going to fill in the random database with values as whenever we get a sample. And we are also going to adjoin to this a weight or some execution score, okay, which is based on scoring that we observe during the execution. And since we are also doing sampling, we have also we also have probability weights, probability density for the execution. So essentially the semantics that we get in the end is going to take the form of a function that takes a state and returns a probability distribution over pairs of made of a state and a weight on some execution score on the execution. Okay, so that's the first semantics that we write. I will skip a few cases of the definition of this semantics. Feel free to ask if you would like me to get back to this later. So, and essentially based on this semantics, we can define some posterior distribution over the state space. So you just have to look at the possible random database that you may observe after you start running the program with some memory that you fix and some empty random database. So you assume that in the beginning no sampling has occurred, which is making sense, of course. So you take the measure defined by some command C and some set of observations A, and you can define it as an integral where you are going to use this memory, so this measure semantics applied to the initial state and empty random database to some set of MRW, to some measurable set of outputs, and you have to also adjoin to this the score of the execution. Like I said, we have this score that has to be carried out. Okay, so essentially at this point we have defined a standard semantics. We can start to work, but we have to do a little bit more in order to be able to formalize SVI in a more appropriate. I mean, we could do it with this definition, but we would like to have a definition that is slightly easier to work with, and also to define essentially semantic condition and also conservative abstract interpretation-based static analysis. So why do we need a second semantics? Well, essentially we have several issues with this semantics. So first of all, as you can see, when we define the posterior distribution, we have the semantics here, and also we have the weight, which appears in a different component. And it would be easier to have to wrap this weight into the measurable semantics. That is not to have to write it as a probability distribution. That's the first problem. And secondly, when we do static analysis, when we do abstract interpretation, very often it's a good idea to start with something that has some clearer operational flavor, because we are going to have to abstract the states that the programs go through, which is not very easy when the result is wrapped into some probability distribution, which is more complex object to abstract. So now we move to a second semantics, which is going to be density semantics. So what is a density semantics? So this time we are going to let the meaning of a program C be described by a function from quadruples to triples to triples. So it takes a state. So recall that a state is a memory state plus a random database. That's why I was saying a quadruple. So actually you have two elements here plus some weight, which is based on the observation based on score, and one more probability, which is essentially induced by the sampling. So in this case, when we finish the execution, we get also such a pair. And to know the weight of the executions, we just have to multiply these two positive real numbers. Okay? So, and the semantics is just a function that takes such an object and returns such an object. As you notice, I also add bottom because we may also have program execution crashes or non-termination. So I am not going through the details about that. But essentially, you may just forget the bottom because in most cases, we hope we don't see that guy. Okay, so now if we look at an example, so here is a small program that will just do a sampling and a score. So you can first do some kind of paper calculation. At this point, we are not doing any analysis yet. We are just trying to see how things work. And essentially, if we start executing the program with some memory and some random database in the beginning with values with weight and density 1, what we are going to get is states of that form here, where we have some value v here I forgot to write. This is you get the set of such elements. Okay. So, and essentially, when we want to compute the overall weighted density, we just have to multiply the two last elements. So essentially, we have a curve of this form based on v, okay, in function of v. So we have a theorem that shows the adequation of the two semantics. So essentially what this theorem says is that the measure semantics of executing C and looking whether we are in A. So we look for the probability to land into A after running C. You can write it as an integral based on the density semantics, and we had already defined it with a slightly more complex integral later. And as you can see, now we have this density function, which is essentially direct output of the density semantic. You just do the product of the last two components, which is what we wanted. Okay? So we now have a second semantics, and we can move on to try to give a definition to variational inference, say when it is correct, and try to find ways to prove that we are in the case where it's correct. Okay, so let's go back to the definition of SVI. So essentially, we would like to minimize some functions. So we are going to identify some family of programs, which is going to be called guide. So I just let them describe by D here. And in order to make the description valid, we are also going to impose a number of conditions. That is, we are going to assume that guides always terminate. So essentially, the measure of when you run guide, any element of guide on any random database, you are always going to get 1. And density should also be 1, so you don't want to have any occurrence of score in the guide, which is these two conditions are very typically satisfied by all the guides you find if you look through the examples in the Pyro implementation. Okay, so and then when we have such a guide, we are going to compute to try to find some optimal theta to minimize this scale divergence, as I said a bit earlier. So now essentially we can look a little bit deeper into how this optimization is done. So essentially, if you look under the hood of SVI, the way it estimates the gradient is using some so if you estimate it based on one example, you have some formula, which I just gave here. And in practice, what is going to happen is we are going to just approximate this using a number of samples. So we do a bunch we sample a bunch of values, and we are going to compute some average here of gradient estimate, which are essentially computed through this formula. So we have one general question here, which is when is this sum of a good estimate of a well-defined gradient for the KL divergence. So that's actually a lot of when. So because we would like to know when we have a good estimate of something that is also when defined. So this is where we get to the next part. So the next part actually boils down to a large set of conditions, which I'm going to summarize here. So we have to have absolute continuity of the density of the guide of the model with respect to that of the guide. So that's essentially what I've shown in the examples. I have shown a case where this was not happening and where this was ending with possible undefined optimization objective. But we have also a bunch of additional conditions that are related to the differentiability of the density of the guide with respect to the parameter theta. Otherwise, optimization will not work, or gradient or stochastic gradient approximation will return biased gradient. You have to also assume that we have bounded KL divergence. You have also to have differentiability of KL divergence with respect to all the arguments, that is essentially with respect to the random variables that are sampled, and also some integral permutation conditions. So these are fairly heavy conditions, and we are very far from conditions that are related to the code. I mean, when people write code, typically they are not just writing, thinking about commutation of integrals or things like that. So a second step goes into identifying conditions that are stronger than that. So we are just going to lose out some programs that we are not going to some pairs and model guide pairs that we are not going to be able to validate because of that. So we have a bunch of syntactic restrictions which are fairly simple and make sense. So we have to assume that we have finitely many control flow branches in the programs and fixed and finite set of sampled random variables. Otherwise, we cannot quite ensure in all cases the previous theorem. We have also this absolute continuity condition for which we are going to build some static analysis. So this is the next step. It is to try to make some automated program verifiers that is going to discharge this absolute continuity. Same for differentiability. And for the last three assumptions, we can also build some static analysis. We are not doing this yet. We are just going to the absolute continuity and differentiability in this work. Okay? Okay, so now let's move on to the analysis. How are we going to do the analysis? Well, we are going to use some formalism, which is abstract interpretation. So some of you may know what it is. So I will recall if you don't know. So essentially, what is abstract interpretation? We are going to start with a reference concrete semantics. So in our case, the reference concrete semantics that we want to abstract is the density semantics. So it's essentially a semantics defined as an element into a lattice of functions. Okay? The second step is to select some family of predicates that I'm going to label as D sharp. So it's essentially this sharp symbol means we are going to use some kind of logical predicates that approximate the elements in D. And this approximation is defined using some concretization function. And what the concretization function does basically is tell us this element of D can be described by that element of D sharp. Also, we have order. So typically, this is up to some order. We also require, although this is not quite a formal requirement, if we just want this to work, we also have to expect for the elements of D sharp to have a good machine representation and also to support good automatic reasoning algorithms. Otherwise, we are never going to be able to compute anything. And based on that, we have to derive a computable and sound abstract semantics that is also labeled with a sharp, and that is such that for each command, it satisfies the soundness condition that the density semantics of C is an element of the concretization of the abstract semantics of C. Okay? And in order to do that, actually, the abstract interpretation framework gives us some kind of techniques in order to build the definition of C sharp based on that of the density semantics. I will give an idea about this in a moment. Before I do, I would like to stress that the result will be computed automatically. So C sharp will be computed automatically. There will be some algorithms that compute it, usually pretty fast. It is going to be sound. That is, it accounts for all behaviors of the program. And it is also incomplete, which means that we may also have an approximation that is so coarse here that actually we are not going to be able to prove anything about C after we do the analysis. So in our case, in order to instantiate that, we can refine this technique, this process, into the requirement of some abstract domain with concretization function and a bunch of operations, which are one describes the empty set, so it is list element, typically called bottom. Widening over-approximates union and allows to also compute in finite time over-approximation for loops. We also have to have an approximation for composition. So if you have two abstract elements, D0 and D1, and you have G0 and G1 in the concretization of D0 and D1, then the composition of G0 and G1 should be in that of the abstract composition of D0 and D1. That is just a general prototype of a sound approximation for one concrete operation. And actually, we have to have the same kind of things for other operations like conditions, assignment, sample, and score operation. Okay? So if we have that, then essentially we derive a static analysis, the definition of which is here, and which is sound. You can prove it by very simple induction based on the structure of the program. Actually, all the soundness requirement is discharged. I put it a little bit for a bit later because I just require for these operators to satisfy some condition. And this is where the hard work goes. Okay, so now let's instantiate this. And to instantiate it, we have to choose a D sharp and algorithm. So we'll do a first analysis, which is static analysis for support and guide match. So we take as abstract predicates bottom, top, plus sets of strings. So basically, we are going to approximate functions using sets of strings. And what these sets of strings describe are essentially sets of sample random variables. And by doing that, essentially what we can do is when we compute some set S, when the analysis returns some set S, we know that the program semantics is a function G such that whenever we run G, the sample dimensions by the program described by G is exactly the set S that we have found out. Okay? I don't give the definition of the transfer function. It follows from the abstraction. So we also have a second instance for differentiability, which also assumes some abstract domains that is a little bit more complex, but not that much more complex. So I will not describe this in more detail here. Now I will just talk for a couple of minutes about the implementation of this in the context of Pyro programs. So when you just try to go from this idealized framework to some implementation, you have to take into account all the problems of the language you're analyzing. In the case of Pyro programs, you have to handle a lot of tensors. So typically, programs will manipulate tensors of high dimension, and they will make a bunch of fancy operations over them. And very often, the random variables that are sampled by the programs are also sampled across tensors. So essentially, in order to get this to work, we also have to approximate states describing sets of dimensions in tensors. So for instance, if you look at this model, which will essentially sample a number of random variables mn samples through a tensor, we have to actually both express precise invariant after the sampling, like when the program finishes, but also in the middle of the iteration. So that part of that work was quite interesting because I just ported some abstraction that I was using to describe programs with complex data structures I've been working on for 10 or 15 years, and I just had to instantiate some of this abstraction just to make the analysis of Pyro programs to work in the context of probabilistic programming. Okay? So maybe I can just comment some results in just 1 minute. So what we did is we just evaluated the analysis on a bunch of programs that are taken from the Pyro web page that include some regression tests plus some larger examples. So we have this series of 8 examples here, and essentially we have the results that are here. So 6 of these were proved correct by our analysis. 2 were not. And actually, if we look at the issues that we have found, so there is the issue that I mentioned earlier in my talk, which was essentially a mismatch of support of the guide, of the model and guide. So that was actually a real bug that was acknowledged by the Pyro team. And there was another one which was a little bit more interesting. So it was a little bit more confusing because in that case we had a model that sampled some kind of random variable that is continuous distribution. And the guide was using discrete distribution. So of course, in this case, you don't have absolute continuity either. And in that case, what the Pyro team told us was quite interesting. They just said, okay, fine. It does not work with SVI, but it's actually defined with other optimization algorithms. So actually, SVI is not the only game in town for optimization. There are others. And that just also opens ways for avenues for future work if we would like to use the same kind of methodology for other methods of optimization. Okay, so thanks a lot.